We are back, and we are going to move into back down to earth with our tangential approaches panel. I will be moderating this one. We have a exciting group of speakers here. Commander David McGlone from the Submarine Safety Program, Dr. Bill Anderson, who does reliability analyses for naval facilities, focused on remote Navy island bases. Joe Miller, who works on the Antarctica McMurdo Station, can speak to the power system there. And then Brian Lee from Centerpoint Energy. So we have microgrids, we have commercial power, DoD, we got everything in this panel. We're going to start it off with Commander McGlone, who's going to speak more or less from a technical standpoint, but more towards the tenets of a high reliability organization. And then we'll go through to our other panelists and open it up for Q&A. So at any point, feel free to drop questions in the Q&A. I'll introduce Commander McGlone really quick. Commander McGlone commissioned in May of 2002 through the Nuclear Propulsion Officer Candidate Program out of Auburn University. He began his Navy career teaching heat transfer and fluid flow and EE to nuclear enlisted and officer students within the nuclear Navy training pipeline. Following completion of this tour, he lateral transferred to the engineering duty officer EDO community. His first EDO tour was at Navy Postgraduate School, where he earned his master's in electrical engineering and completed total ship systems engineering program. From there, he completed a strategic patrol on USS Wyoming. He then reported for qualification tour at Norfolk Naval Shipyard, and he was the engineering duty officer in engineering duty officer qualifications while serving as ship safety officer and nuclear assistant project superintendent during USS Tennessee's engineered refueling overhaul. While at Norfolk Naval Shipyard, he also completed a 9-month tour as an individual augmentee supporting NATO efforts in Afghanistan. He later served as depot budget and scheduling officer at Commander Submarine Forces Pacific Fleet, and then transferred to Pearl Harbor Naval Shipyard, serving as Deputy Project Superintendent for U.S. Olympia's fiscal year 15 maintenance availability, later as Project Superintendent for USS Chicago's FY18 avail. And Commander McGlone assumed duties as the Navy Submarine Safety Program Director just earlier this year. So Commander McGlone, thank you for joining us, and I will drive your slides and take it away.
Hey, thanks, Matt. Can you hear me?
We hear you just fine.
Okay, perfect. Yeah, hey, so when Matt reached out to me as the Submarine Safety and Quality Assurance Director for the Navy, I thought, man, how am I gonna have this discussion relative to an electric power grid on the moon? Anyway, so centered up on high reliability organizations, because that's what we are. Ultimately, next slide. I just want to talk briefly with you about the purpose of the program, safety program fundamentals, the subsafe program itself and the origination, and then high reliability organization. And I'll leave you with a couple of final thoughts. And I really appreciate the opportunity to speak to you guys today. So the purpose of the submarine safety program is to provide maximal reasonable assurance of the hull integrity to preclude flooding and of the operability integrity of critical systems components to control and recover from a flooding casualty and ensure the safety of all sailors aboard subsafe fly-by-wire ship control system and deep submergence system certified assets. Next slide. So first of its class, USS Thresher, SSN 593, launched in 1960, leading edge of submarine technology at the time, nuclear power warship. It combined nuclear power with modern hull design and newly designed equipment and components. Next slide. On 10 April of 1963, coming out of a more or less a warranty or a guarantee period, maintenance period following delivery, USS Thresher was out on sea trials. And she was engaged in a deep test dive approximately 200 miles off the northeastern coast of the United States. And then the Thresher was lost at sea. They lost comms, and all 112 naval personnel and the 17 civilians on board were lost. And out of this loss came the inception of the SubSafe program. Next slide. During that investigation, there were some immediate responses within the Navy, and then obviously there was some, investigation and whatnot. So the diving depths of all submarines was limited. Court of inquiry was convened, and then there was lots of testimony and report to Congress at Thresher Design Appraisal Board, where they focused on the design, construction, and operation. Next slide. They came to the conclusion, no absolute definitive, we know this for a fact, the most probable cause was flooding in the engine room, unable to secure from the flooding, spray on electrical switchboards, loss of propulsion, and then unable to blow the main ballast tanks. And the ballast tanks are the big tanks that provide positive buoyancy when you evacuate the water from them. Next slide. The conclusions were there were deficient specifications, there were some design changes made, deficient shipbuilding and maintenance programs. For example, at the time there was a lot of silver brazing, and wasn't considered to be the greatest bonding. And then NDT types of discussion, deficient operational procedures, and then incomplete or non-existent records for work accomplished, the critical materials and the critical processes, and marginal rescue capability. Next slide. I wanted to throw some excerpts in here from the Thresher testimony where Senator Curtis, is it oversimplification to ask why the work is of such poor quality? And Admiral Rickover, who was the director for the Naval Nuclear Propulsion Program at the time, for many years, in fact, and often coined the father of the nuclear navy. No, I think that it is a logical question. I think people just did not believe that adherence to the specification was necessary. And then Senator Curtis, was it a careless attitude on the part of the workmen? And Admiral Rickover says, careless attitude, in my opinion, on the part of all concerned. I don't believe you can blame the workmen alone. All of the workmen have a man over them. This is a foreman. There are officers in the field. If I have a job to do and it doesn't get done well, I'm not going to blame the workmen. Next slide. So out of this was introduced the SubSafe manual, first introduced 20 December 1974, and it has a whole list of requirements here from administrative, organizational, technical, design, material control, fabrication testing, audit, certification, work control, et cetera. And this is what I spend most of my time auditing activities to ensure that they're in compliance with. And of course, we continue to advance this manual with the latest and greatest as we discover different issues here and there. The program fundamentals, next slide, please. The program fundamentals really are in the areas of work discipline where there's knowledge of requirements, adherence to the requirements, due diligence, material control, is the correct material installed, and is it installed correctly? And there's a whole litany of requirements that go with that. We have a level 1 program, and there's strict chemical and tensile properties for various materials, et cetera. Documentation, design products, specification, drawing, maintenance standards, and with everything that we do in the SubSafe program, there's objective quality evidence that comes with that to demonstrate adherence to these principles. Compliance verification, I'll do a couple of different types of audits: inspections, surveillances, assessments, technical reviews, and then we really kind of focus on the culture. And I'll come back to this one in a minute, but it's focused on lessons learned, deficiency trends, a healthy obsession with the consequence of failure, proactive correction, prevention of problems, and adherence to program fundamentals. Next slide. The safety culture foundational elements, responsibility, a duty, obligation, or burden, accountability, the state of being answerable for one's actions, and then integrity, rigid adherence to a code of behavior. Next slide. So multi-layered approach, as you can imagine, with the number of submarines that we have and new construction and different flights and classes and different maintenance activities, both private and public, and all sorts of different vendors feeding every part of this, it requires some pretty rigorous evaluation and control. So multi-layered approach, the contractor shipyard activity responsibilities, there'll be inspection, surveillance, document reviews, audits within those activities themselves. There's the local government oversight authority responsibilities, And then there's headquarters responsibilities, and I do a lot of audits, and we're ultimately responsible for certifying these submarines either back to the fleet or to the fleet when they're delivered from new construction. Multifaceted approach, the ship system certification audits and the facility functional audit. So again, two parts, the ship or the system certification audit, and we do this for submarine safety, fly-by-wire ship control system, and deep submergence. We're validating the material condition that it adheres to the requirements for a specific asset. The facility functional audits, we want to make sure that whatever activities we're going to audit, that they're that they've got the right cultural standards, that the process is in place, that they're adhering to them, et cetera. And there's two different types of audits. They'll audit themselves and do an internal audit, and then we'll come in as we'll sort of oversight, independent oversight, and we'll do an external audit of the activity and help them there too. Next slide. And this is what I was just talking about. The certification audits are ship specific, and again, we'll deep dive the material at close to the end of every availability or every delivery. We will deep dive every aspect of the material condition of a submarine to ensure that it complies with what we expect it to comply with, materially, design, et cetera. Testing, everything. And then the functional audits look at the activities. And then the functional audits build the foundation for certification. Next slide. Everything that we talked about, there's the design certification, the material certification, again, the chemical, physical, process, NDT, fabrication. Did we do the right NDT? Did we evaluate it correctly? Did we execute the process? Were the people qualified to do the work? Was the equipment qualified to perform the work? And then testing the strength, tightness, and the operational system operational objective quality evidence. Next slide. And the cultural challenges that we constantly face, just as human beings. You know, there's the arrogance, habit of behaving based on pride, self-importance, conceit. We're better than everybody else. That's when things, you know, when you're starting to creep in the wrong direction from a cultural perspective. There's complacency, where you're satisfied with your accomplishments, accompanied by a lack of awareness of actual dangers or deficiencies. If you're not moving forward, you're moving backward. Ignorance, the state of not knowing, and then denial, the refusal to see the facts clearly in evidence. The success of the program, next slide, please. Success of the program from 1915 to 1963, 16 submarines, 454 lives were lost to non-combat issues. From 1963 to the present, we've lost one submarine. It was the USS Scorpion in 1968, and that was not a subsafe certified boat. This is really trying to demonstrate the success of this program. And, you know, we've even had some in the press, you've seen them, some casualties in the past and significant casualties. And as a result of this subsafe program, it's stepped up the material assurance of these assets to the point where they were recoverable, even in those conditions. Next slide. And then I wanted to share, you know, high reliability organization principles. And so there's the sensitivity to operations, the heightened awareness of the state of relevant systems and processes, the reluctance to simplify, such as, you know, trying to get everything onto a game controller, acceptance that work is complex with the potential to fail in new and unexpected ways. Simplification is not a bad thing, provided that you recognize that everything behind it has a complexity that needs to be considered. Preoccupation with failure. Don't view near misses as as proof of success. There are opportunities to instead improve. Deference to expertise, to value the insight from staff with the most pertinent safety knowledge over those with greater seniority. You know, I'll just pull the Challenger discussion into this for a minute. The subsafe program, we've supported the safe space program in the past years ago with that, to bring it to space here for a second, the Challenger event. And one of the things that I'm sure is on the forefront of your minds, you know, from a memory perspective is, you know, the culture at the time was prove to me that it's not safe. rather than prove to me that it is safe. And there's a huge difference between those two approaches. And so, you know, it's that sensitivity to the operations. And lastly, practicing resilience, prioritize emergent training for many unlikely but possible system failures. And I can tell you that, you know, from a Navy perspective, emergency response training is huge. It's believed that our belief is that, you know, practicing emergency response drives into the normal day-to-day cultural aspect of how we get stuff done just generally, in addition to response to emergency. Next slide, please. And the last thing that I'll leave you with is again, another quote from Admiral Rickover. Good ideas are not adopted automatically. They must be driven into practice with courageous impatience. Once implemented, they can be easily overturned or subverted through apathy or lack of follow-up, so continuous effort is required. Too often, important problems are recognized, but no one's willing to sustain the effort needed to solve them. And this is kind of a cultural discussion, right? You can change a procedure in writing, and maybe something changes the next day, but that doesn't change the culture of an organization to start thinking, you know, very critically about safety challenges and dissatisfaction with failure and how we're going to, you know, improve on those kinds of things. It doesn't just come from writing something down in a procedure. All levels of leadership focus on that kind of mentality. So anyway, appreciate the opportunity to chat with you about high reliability organizations in my program.
Thank you so much, Commander McGlone. We really appreciate your perspective here. So feel free to put questions for Commander McGlone in the chat, and we'll bring all those up in the Q&A at the end of this. And I'll introduce our next speaker, Dr. Bill Anderson. Oh my, advanced your slide accidentally. Bill Anderson is the Director of Utilities Engineering Management Division for Naval Facilities Engineering and Expeditionary Warfare Center in Port Hueneme, California, and leads a microgrid team to develop more climate resilience globally at naval installations. Bill founded and operates the Navy's microgrid testbed and the Microgrid Academy. Bill is formerly a management consultant with McKinsey & Company and a retired career U.S. Naval Civil Engineering Corps officer. Bill is a licensed professional engineer, and his PhD is in systems engineering from Naval Postgraduate School. Bill, take it away.
Yeah, thanks, Matt. And Matt, if you could be so kind to go to the first slide. Thanks. So, yes, I'm in Port Hueneme, and that's in Southern California. As Matt said, I'm laser focused on microgrids, and what I'm going to share with you is rather technical in terms of what we are doing for naval installations. These are the 70 plus installations globally, primarily focused on what we call our islanded naval installations, remote islanded sites, a la Diego Garcia in the middle of the Indian Ocean, San Nicolas Island off California, as well as a handful of other sites around the world. And that's our focus, and very much what got us into the work that we did for National Science Foundation in Antarctica, which led me to what I'm doing now for this session. So I want to draw your attention to this graph, and this graph is a graph that I developed for our team to use, and it's what we call our microgrid resilience curve. And what, you know, again, resilience, I just want to emphasize, we are very much focused on resilience. We recognize and have been focused on reliability as a priority for our power systems, but we're focused on resilience, and we're focused on that for a number of reasons, primarily because of climate change, but also due to cyber attacks. And all of those are in that category that we consider high impact, low probability events. So that focus on resilience is what led us to develop this curve that allows us to measure resilience, assess resilience, and provide a trade space for decision makers. So it's important that we understand this curve. This curve on the y-axis represents the performance of the microgrid, and the x-axis is time, and we divided those time dimensions into 5 phases: the pre-disturbance state all the way to the post-disturbance state. And this blue curve that you're seeing on this graph represents the performance of the microgrid over time. You'll see a highlight of 2 metrics or measures that we use to get to our resilience score: the recovery measure, which is over time, and then the invulnerability measure, which is a measure of the unmet demand that's a resultant amount due to a extreme event. So that extreme event happens right after the pre-disturbance state and before the degradation state. And that's where you see the curve drop until it gets to a stabilization state, and then it comes back up over time in the recovery state till it gets to its post-disturbance state. So we're using those 2 measures, our models that I'll get into a little bit, replicate over time this curve for any microgrid architecture. Next slide, please. Okay, so what I want to give you a sense of is what we do for the Navy with our tools. And if you look at the top left, it gives you a sense of what we're trying to do, and we are doing for the Navy, using our tools that we've developed to provide this end product, which is the graph you see on the right, to decision makers. That's based on our tools and our methodology to provide assessments of notional microgrid architectures so that we can better inform decisions centered around more resilient and more cost-effective solutions. And as mentioned, we've done assessments in Antarctica, San Nicolas Island, recently Rota. I'm working on one in the Suda Bay, Crete. I was there a few weeks ago doing that with my team, and getting ready next month to work again in Micronesia at island sites for microgrid solutions. And then if you look at the bottom left there, I'm drawing your attention to the significance of our tools, and that is so that we can put a cost on resilience. And we developed our own cost measures. We adapted an industry standard for us, which I also think is applicable to anything done in a situation like you're considering on the moon, and that's a life cycle cost of energy for demand. And more importantly, we've incorporated different levels of maintenance into our models, and allows us to assess resilience versus previous assessments were more focused on reliability. That top graph in the right, that's our end product. It's a 4D graph, fourth dimension being this is what we provide as a result of our models. And I can get into that more later, but basically this one you see was done for San Nicolas Island. And the WTs are the wind turbines, 5 each 100 kilowatts. The DGs are the diesel gensets, each 1 megawatt. Y-axis resilience, and again, the color is the life cycle cost of energy over time. Down the bottom right, I'll just draw your attention. We did this for the air terminal at Rota, and use assessment for an architecture, a design solution of microgrids at a quarter of the life cycle cost using this approach. Next slide, please. So this slide is meant to draw your attention to 2 things. One, on the left, our 3-step methodology. And our methodology is such that we first start with a site. And this is a site that has been chosen, obviously, to potentially put a microgrid in. And we optimize a solution using a optimization engine. Presently, we're using a tool called Zendy, and we're optimizing that with an objective function to minimize lifecycle cost. Once we have that optimized solution, we create design variance on that, hovering around roughly a 10% deviation from the quantity and capacity of the distributed energy resources. So we have a roughly 30 to 40 different architectures that we then run through our resilience and cost assessment tool to get a resilience score and cost score for each of the design variants that we then in MATLAB, we create the 4D graph that I showed you earlier. And then I wanted to draw your attention to the graph on the right. This is a graph that we've done, that we've developed using our models and tools and methodology to show the relationship in excess power capacity, the power generation, power capacity demand ratio that you see going on the x-axis from 1.25 to 5 versus resilience versus cost, and there's a maintenance dimension in there as well. We've also done this for redundancy, and it has the potential to do it for other meaningful ratios as well. So I think that's my last slide.
Perfect. Thank you very much, Bill. And anyone that has questions for Bill, feel free to put them in the Q&A, and we'll ask them after our other panelists introduce themselves. So now I'm going to introduce our next panelist, Joe Miller, and you can go ahead and share your screen to drive your slides, and just let me know if you can't share. I can share them for you. Joe Miller, there we go. We see him right there. Joe Miller is an experienced facilities operator and maintenance leader, believes that well-documented, realistic maintenance plans, maintenance staff training, and smart equipment selection and management buy-in are key elements to operate a facility reliably. Joe has built his career in improving maintenance programs and increasing facility and utility reliability on large campuses operated by the Department of Defense and major universities. Joe is currently the Facilities Construction and Maintenance Program Manager for the U.S. Antarctic Program, operated by the NSF. He has responsibility for the ongoing operation of the facility and utility systems at the United States' 3 permanent year-round research stations in Antarctica. First got hooked on Antarctica when he wintered over as facilities engineer at McMurdo and saw firsthand the challenges created by the environment and logistics. He has a master's and bachelor's in mechanical engineering from Georgia Tech and is a licensed professional engineer. And take it away, Joe. Thanks for joining us.
Yeah, thanks, Matt. So just like Matt said, I'm an operations and maintenance guy, so I'm going to keep it pretty high level, and we'll save some time for the Q&A at the end. So just a quick overview of our U.S. Antarctic program. So we operate 3 stations in Antarctica: Palmer Station on the peninsula side beneath South America, McMurdo Station beneath New Zealand, and the South Pole Station in the center of the continent. So Palmer and McMurdo are both accessible by vessel. We operate a series of military and commercial aircraft and vessels to resupply our stations with participants and with materials and fuel. So the South Pole Station, we resupply it with military aircraft, or we do a overland traverse about 900 miles and 10,000 feet of elevation gain from McMurdo Station to the South Pole Station. We do 3 of those per year. So we've been operating these stations in Antarctica since 1959. So we got a little bit of history there. So just a deeper dive into the stations. So they're sized about proportionate to the resources that they require. So McMurdo Station is our largest station. So talking about power, the average demand over the years about 1,500 kilowatts. Power station is down near the water, and we distribute power through several different pathways, but generally overhead. And the end-to-end span on our distribution system is about 5 kilometers on this site. Edmonton South Pole Station has an average demand of about 600 kilowatts. The maximum occupancy at South Pole Station is about 150. We're currently in the winter at all our Antarctic stations, so there's about 40 people at South Pole Station now. We are limited by logistically by how much fuel we can move to South Pole Station in our window to get there. We really only have about 3.5 months that we have access to the site to move materials. And Palmer Station on the peninsula side, that's our smallest station. Average demand is about 125 kilowatts, and the maximum occupancy there is about 40 people. But this one's unique in that we don't have access to it by aircraft. So it's about a 4-day ship ride from the bottom of South America to get to Palmer Station. So I'll just add, in addition, we operate a variety of smaller seasonal field camps. So I heard earlier about the Artemis clusters and the size of those. So our field camps are very similar in size. So between 5 and 50 kilowatts of power demand for those. Some of them are seasonal, operated only in the summer season. And then we also have some communication sites that are monitored and operated throughout the year, even when we can't get to them. So just a couple of our pictures of some of our systems that are across Antarctica. So we rely pretty much on high maturity, pretty reliable technology. So at the 3 stations, our primary power source is going to be diesel electric generators. We use combined heat and power. So we are recovering the heat to heat a good portion of our facilities. And our distribution on the stations depends on the operational needs of the station and the ground that they're on. But we do use overhead distribution. We do have ground laid cable and also buried wire. So South Pole Station is actually on a 10,000 feet thick ice sheet. And so we trench into the ice sheet and we bury our cables under the ice sheet. But from a maintenance perspective, our ice sheet is moving in 2 directions and it moves a pretty good amount every year. So our longest run of cable at South Pole Station is about 10 kilometers. And so when they install that, they have a huge vault that they dig and they loop an expansion loop. And so one of the problems with maintenance there is that installation's been in a long time, but now we've stretched our cable. So we're currently working on how long do we have before we need to redo that cable. And we're installing a hot water trencher to be able to trench the future electrical cables through that ice. We used to use traditional trenching methods, but that we found that they were too risky. And we actually, just like you would in the continental United States, we hit stuff when we start trenching with big mechanical equipment. So hot water is going to be safer. And then we're working to reduce our logistical footprint. So the Antarctic operations are driven by logistics, just like trying to get heavy stuff to the moon. It's not as bad in Antarctica. We have ships and planes, but the majority of our fuel use is spent transporting materials to Antarctica. So we're trying to reduce the need to do that. And part of that is to increase our use of renewables. So our field campsites, so we have about 50 designated field campsites that are not all operational every year, but those field camps are usually, because they're much more remote and they require specific planes and helicopters and other things to get there, we rely much more heavily on wind and solar and battery backup storage for those locations. And then at McMurdo Station, we operate that grid in conjunction with Antarctica, New Zealand. So one side of the grid is the Antarctic New Zealand station, which operates on 50 hertz power. And then on the other end of that is the McMurdo Station operating on 60 hertz power. But in the middle, Antarctica, New Zealand operates 3 wind turbines, which give us a pretty good contribution of our power. And then kind of in forums like this, all the Antarctic programs get together and we're talking about how can we continue to use these different power methods reliably. So the Antarctica in itself, even though the conditions are very harsh, high winds, very cold, but we're outside of the traditional market and we don't have enough demand to create our own market. So we're often trialing and error and finding some success with small vendors who are interested in the challenge. Sorry. And So we collaborate with our international partners and try to find things that work and methods and operations that work well for Antarctica, and start trying to do those. But in a reliability standpoint, while we're still introducing new technologies, we're still relying and having that backup of those fuel-fired, highly reliable pieces of equipment. And then just because the forum has people that are interested, we're currently working on doing a new master plan for the South Pole to talk about the next couple of decades. So a little advertisement here for anybody that's interested. We'll be hosting 4 sessions coming up in August to talk about the future of the South Pole. So that'll include our science community, but also the public and interested parties are welcome to attend and make their stamp on the South Pole Station. And you can register at the URL that's on the screen if you're interested, and the agenda for those sessions is available on that site.
Oh, that was really cool. Thank you, Joe. That's
Yeah.
certainly a very extreme environment to operate in, and we're getting a lot of questions now in the chat. So we will we'll introduce our next panelist, and then we will probably go to the breakout sessions around 3. So we'll keep this panel going until about 3 o'clock, and then move on to the next session. So I'm going to go ahead and share Brian's slides for him. Brian, you can go ahead and unmute. Brian Lee is joining us from CenterPoint Energy. I wanted to go ahead and introduce yourself and tell us about how the commercial power industry deals with these problems.
Yeah, I'm the dumb utility guy in the room. And so Brian Lee, a bachelor's and master's degree in electrical engineering from the University of Houston, go Cougs. I got 7.5 years of experience here at CenterPoint Energy, both in transmission and distribution side of the company, dealing with relay protection schemes, and now in power quality and reliability, interfacing with our customers here in the greater Houston area. So a lot of what's been done so far from the 3 previous presenters are very highly controlled systems, or remote islands, or Antarctic regions, very harsh remote areas. Everything's very controlled other than the elements. But with the utility, you have to, accommodate all sorts of players. And one of the things that we're discussing about the lunar grid was, well, how do you interface with China or Russia? And, how do you make sure everyone meets the same standards? And, you can't control what they're doing. They can't control what you're doing. So how do you set up a mutual agreement that you're going to abide by certain standards, right? And that's a little bit what I'm going to talk about today. So if we go to the next slide, just kind of going over the, this is, courtesy of NASA, thank you for this picture. This is our grid here in the city of Houston, Texas. We serve 2.8 million meters, and our peak load is about 19.4 gigawatts and growing with this recent string of record heat. So, and continuing to grow, right? So we can go to the next slide here. I'm going to talk about general system overview, as our special underground networks that we have here in Houston. Some of the key grid components we have, just to understand what do we have on a distribution grid, how do we plan out a distribution grid, and how do we enforce standards for customer interconnections, or any interconnection between utilities, right? Tie lines. So let's keep going. Right, everyone here is aware of the transmission, distribution, substation. Generators create electricity, steps it up to high voltage to reduce losses. Then we step it back down to a usable form of power through our distribution system. Keep going. So we currently maintain at least 28,000 miles of overhead circuit in the greater Houston area, 24,000 miles of underground circuit, 19 gigawatts of peak load and growing, 2.8 million meters and growing, served from 2 different primary service distribution voltages. So we cover everything from Freeport, Texas to the Woodlands, from Baytown to Sealy. Next slide, please. So, we have our standard overhead wood poles that, you see every day. So something special that we do have that you may not see every day is our underground network. So if you're in downtown Houston, you have no idea this is there. You don't see any wood poles in downtown Houston. So not only is it underground, it's also a network system. Most of our distribution overhead circuits are radially fed. However, the downtown network, it's supposed to be always on. If anything goes out, that isolated circuit, will not impact the reliability and of the affected customer, because they're still connected to 4 other circuits, right, through this network. So the highly dense network, the issue with the network system is it does create higher costs for our customers in the area because of the increased arc flash, and they have to abide by higher safety standards. So, to maintain affordable electricity for our customers, we can make them install, 24,000 amp panels rated, it's just excessive costs. So very small specialized area where highly controlled vaults, highly controlled underground vaults in order to serve these customers. Next slide, please. So just some general understanding of what's on a distribution grid, right? Things that we need to maintain and operate. We need to make sure we can operate and maintain switches, make sure they're next to the roads. They're not in any back alley that our crews can't get to. If you kind of click through these slides, some pictures will show up, right? That's an example of a switch that our crews can operate and maintain. So these are used for moving load around. We also have fuses to protect and isolate against faults on the grid. Keep going. Reclosers. So these are automated intelligent devices that can automatically close, isolate, reclose, transfer load between circuits automatically across large distances. Capacitor banks in order to maintain power quality and unity power factor for the circuit, to reduce loading on the circuit more towards unity. Regulators to boost the voltage for distant customers in the air. Sometimes we have circuits over 70 miles long. So in order to maintain voltage for all these customers with a voltage drop, we install a lot of regulators in those remote rural areas. Of course, we also have the step down transformers to step down voltage or step up voltage to specific customers, depending on if they're in 12 kV served areas, but they need 35 kV primary service voltage. And the smart meters, 2.8 million smart meters in the city of Houston, where we have a collection engine to manage this massive amount of big data. And every 15 minutes, we're getting voltage loading data. And one thing we're trying to do with this smart data is we have all this data, but how do we actually use it to our advantage? And wrangling this beast is one of our long-term goals to, how do you track voltage issues along a 72-mile circuit? Well, these meters, they have GPS coordinates, they have, the voltage profile. So now we have voltage profile maps for the system. Which phase is the problem? We can pinpoint issues, which typically took us 5 hours to identify. Now it takes us at the click of a button. It already knows where the issue is, right? Through this automated, so the more we automate using the smart meters, and we're still continuing to find ways to improve. So with a continuously growing system, we have to plan for the future, right? Make sure we can accommodate all this load. We have a very robust GIS system with, you know, I think every utility always deals with GIS data quality problems, right? Oh, this is the wrong GPS coordinate, or this is assigned to the incorrect connection node, right? So a lot of AI is being worked on right now to make sure that the data quality issues can be cleaned up much faster. We model both AC and DC systems for these almost, I think we have just one of our big battery developers. We have 300 megawatts slated just for the Houston area. So we do model these giant batteries. I mean, 10 megawatt batteries, right? Is the limit for distribution before they need to upgrade to transmission systems. And just one of the developers already has 300 megawatts just in the city of Houston, or the greater Houston area. And so we use the SIME modeling software to model voltage drop, loading capacities, contingency studies. However, what's not in this model is environmental conditions, right? Is the truck accessible? Those kinds of characteristics aren't really easily automated, right? Unless we have some sort of, so there's additional work going into that space. As well as material specifications, right? What's the exact material that's on this conductor? Not all of that's well modeled. Continue.
You could try and wrap up in the next minute or two, Brian.
Thank you. Okay, and so we try to plan out for our load for over 10 years, and depending on new master plan developments, new customers coming in, we need to make sure that we can meet this load. So we development plans in order to accommodate the future capacity and not just handle the load, but also handle any failures. So if one circuit goes out, the other circuit needs to be able to handle the failed circuit, right? So keep going. And this is the last part. Any customer that connects to our grid, we need to make sure that they meet all these standards. They're not just connecting to us, we're connecting to them also, right? So we need to make sure they don't cause motor start flicker, they don't cause harmonic issues in the area. Their distributed generator doesn't cause any over voltage or back energizes any faulted equipment. They can ride through voltage sags, and any automated rollovers or load transfers can be safely handled by the adjacent circuits. So that's kind of just overview of the distribution system, super quick, from the utility space.
Thanks so much, Brian. We appreciate it. And I also appreciate all our panelists going and answering questions as they've been coming in the Q&A. I'm just gonna bring up some of these in the final kind of 10 minutes of this panel. First question, Bill already answered this in the chat, but I'd like you to kind of speak to it for everyone. Leonardo asked if the optimization approach allows for multiple decision makers or perhaps conflicting objectives. You there, Bill? Bill's in the UK, so he's on a little bit of a time delay. You are.
Yeah, all good. I'm tracking you. Yes. But
we're hearing you come in and out, Bill. You might want to try turning your camera off if you're bandwidth limited.
Optimization, and I think I should consider bandwidth now. No, can you hear me?
There you go. That did the trick.
Is that any better? Okay, so short answer is we can, but we choose not to, because a multi-objective optimization will likely create non-feasible solutions. So the work we've done on that is the trade space we create, which accomplishes more or less a similar solution. And trade space, we are showing competing objectives. Resilient cost, we can adapt that to climate resilience cost. Not doing that, but yes, we could.
Thanks, Bill. Gonna ask this question from Yafan for Joe. Given the low operating temperatures, what kind of batteries are used and needed to support the renewables in Antarctica? This is very applicable to the moon.
Yeah, so the small remote sites that are likely to get really cold, we still use sealed lead acid AGM type batteries. They can trickle discharge even at low temperatures and keep some electronics alive, even if they can't accept a charge, and we just are able to oversize them and carry on a little bit longer. For more complex chemistries, especially lithium chemistries, then we're putting them in enclosures that have backup power systems to keep them warm. That if we lose power, then we'll keep those batteries above freezing. Or we have backup. If our power systems fail, we have fuel fire backup heaters, and we'll have operational people that can go apply that heat to the building to keep those batteries above their temperature range.
Thanks, Joe. I had a question for Commander McGlone I wanted to ask. So how do you see the subsafe ethos filtering down to technology development? Is this inherently heavy on risk? Perhaps you answered this with your ending quote of needing for courageous impatience.
Hey, Matt. So from a technology development perspective, I mean, I would tell you that we're building and design. We've just recently designed a new submarine, the Columbia class. There's a lot of new technology there. Some of it is not necessarily in my purview from a subsafe perspective, but a lot of it is. And what I'm interested in is making sure that once the design specifications are defined, I want to make sure that they're adhered to. And part of the design specification has to do a little bit with, expected failures, right? So we have a class maintenance plan. We'll schedule replacements of things prior to failure. Sometimes we don't always get it right, but the bottom line is that from a technology perspective, to keep these things operational, we have a scheduled maintenance plan. The other technology to discuss technology insertion, part of my portfolio is also the fly-by-wire ship control system or ship control station. And our new submarines, they are driven by fly-by-wire computers. And there's a whole process of certifying those aspects of the system. And I suspect that for your lunar model, there's going to be some level of networking and centralization of information flow and whatnot. And I found it interesting, the gentleman talking about the speed of information from the Texas power grid. But anyway, there's a lot of effort that goes into designing the fly-by-wire system, certifying the activity that does it, reviewing the code that is developed to ensure that it operates the way we expect, and then before it ever gets installed on a ship control system on a submarine, it's certified. Anyway.
Thanks, sir. Really appreciate it. Question for Brian that came up in the chat. Do your AC/DC models allow for natural hazards, electromagnetic events, and other contingencies explicitly?
So we have multiple software models to model the transmission grid, the distribution grid separately. We recently had a case where we had 3 miles of transmission line inducing voltage into our distribution lines. And in order to, fully model that impact, we had to extract the data from the transmission model data, distribution model data into PSCAD. And, we measured the angle shifts that was causing one of our clients to see, excessive voltage unbounds due to this induced voltage from the transmission system into the distribution system. Both models are capable of modeling mutual coupling. However, it's just the 2 disparate systems, right? In order to also model the induced voltage, we decided PSCAD was the best way to go for electromagnetic, which will also help you model electromagnetic events, right? Like EMP shielding or EMP issues.
Thanks, Brian. All right, so we are about 15 minutes over. I wanted to leave with one last question before we move on to our breakout sessions. Really for Bill and Joe specifically, who deal with the most remote applications that are most lunar akin, what lessons learned do you have that you think that could be easily transferred to the lunar surface? Things like logistics, spare parts, maintenance. How do we engineer things so that it can be consistently maintained on the lunar surface in just a minute or so?
Yeah, this is Bill. I'll take a quick crack. We've learned through our models that predictive maintenance is both better than preventive maintenance. One for cost and reliability, but more importantly for resilience. So getting into the forecasting and predictive maintenance. And the last part is we've learned that redundancy is good, and the power ratio beyond excess power ratio of 1.5, 2 has little benefit for resilience.
And I'll just say that,
Joe, you're muted.
yeah.
John, you may need to mute too.
So I'd just say, similar to what Bill said, so we're looking at, as we get increased bandwidth in Antarctica, we're looking at how we can use controls and other sensors to do predictive maintenance and to schedule our maintenance so that we're not always sending eyes out into the field to do that. And then I would just say plan for failure, know that you're going to have problems, and plan your systems so that you have a cascading options as systems break down to keep your crew safe and keep your mission going along.
Thanks, Joe. John, did you want to say something real quick?
Yes, a question for Bill Anderson. If we can get it, a succinct definition of the difference between resiliency and reliability.
Yep. So there's a fork in the road in the two.
Okay.
I'm getting some feedback. Somebody has open mic. Okay, so there's the fork in the road of the two. Resilience is we're dealing with high impact, low probability events. And basically it's how quickly you can recover from something like that. Whereas reliability is dealing with low impact, high probability events. And what we've also learned, reference the moon, is that a design solution for resilience is not the same as reliability. There's a sweet spot between the two, which we're trying to better understand, but those are two different solutions. And I have to say this because Texas came up. ERCOT, hence the R in the name, reliability, was very much prepared for reliability events, not resilience. And that's what we're very much driving to help inform solutions for resilience to deal with those climate-driven events and cyber attacks.
Well, yes, I experienced that, the Texas example you just mentioned. But is it fair to say that maybe resilience deals with externally driven failures and reliability deals with internally driven failures to the system?
No, I would not say that's fair. Yeah, no. If you stay unmuted, okay. So the difference, again, the example I give is power lines and transmission lines. You can have a power line that's above ground, which is very resilient because it's easy to repair, but not reliable above ground because it's more subject to weather degradation and so forth. Whereas if it's below ground, it's the inverse. But it's not internal. I mean, both are subject to similar events that cause degradation of equipment. It's just a matter of the extremeness of the event in terms of impact, as well as the ability to predict the event.
Thank you very much, Bill. And I think that's a good note to end on and move into our breakout sessions as we're well over time. And I'd like to thank all four of our panelists. Joe had to drop off, but thank you, Bill, Commander McGlone, And Brian, we really appreciate your insights. So now I'm going to introduce our breakout sessions that we're about to go into. So we're going to go into a separate Zoom link, which was sent out in the email that I sent yesterday that had this Zoom link that you joined via. We're going to drop it in the chat here too. We have a QR code too to get you to the right place. Will be an APL facilitator in each of these Zoom rooms that you're going to go into to help drive the conversation via a Miro board. Some of the big things we want to keep in mind, we want to get this stuff written down. Any of your feedback, any of your insights, if it's not written down on a note in the board, it doesn't exist. So we're going for breadth, and we're trying to find consensus here. So just, think big and make sure, everything is written down, and acronyms, define them. And obviously let's try and keep this all ITAR and public release compliant. What we're gonna do, we have basically 3 separate tracks, and there'll be 2 rooms for each track that you can go into. One's gonna start discussing power generation, one will start on energy storage, and one will start on distribution. If you make your way through the questions on that topic, your room can move on to one of the other topics. If not, if you just want to discuss the first question the whole time, that's totally fine. You'll be randomly put into rooms, but if you really do not want to be in the room you're in, you can leave that room, and there'll be an APL facilitator outside in the main Zoom that can place you into one that you might be more interested in. And then we'll summarize the major takeaways from our discussion at the beginning of the meeting tomorrow at 11 Eastern time. It's pretty easy to navigate the Miro board if you haven't done it before. Up and down arrows like you're on an old video game, and your scroll wheel could take you in and out. That's really all you need to know. And then when I say, make sure everything's written down, you can see here, we'll have a whole bunch of these different colored sticky notes already pre-populated that you can just click on and make bigger and start writing stuff that you want to leave. Or you can, click on the sticky note bar on the left side of your panel and get more for yourself. So that's the link that you're looking for. This QR code will get you there. Andrew should be dropping it into the chat. Our APL facilitators can start making their way there, make sure everyone's in a room, and we hope that everyone can stick around. This is your time to get your feedback into us so that we can get it up to NASA. And thanks again for everyone who took the time out of their day to join us. I'll keep this up for a few seconds. Hopefully everyone's starting to leave this meeting and make their way into the other Zoom link. And then I will drop off, and we'll close this here shortly as people start dropping off. And this will be the end of this Zoom link. We will not be reconvening here afterwards. There will be a separate Zoom webinar link for tomorrow. So once you're done with the breakout session, we're done for the day. All right, I'm going to give it a few more seconds. People are leaving. And all right, I'm going to stop my share and drop off. And Andrea, thanks so much for your help. We can go ahead and kill this webinar.
Thank you, sir. Garrett, we're set to close.